Hi, my name is Ian Swett, and I'm here to talk to you about a new type of outage that we discovered at Google. I've been a Google engineer for over 10 years, with most of the time tech leading and managing a team that works on QUIC, HTTP3, and other web protocols. They're all focused on both protocol development as well as web performance, with a huge focus on user-facing traffic, not internal traffic. We take reliability extremely seriously, and our team looks at every single crash, even if it only happens once. Most of the time, a single crash is just a bad machine or something, but every once in a while, it's a 0-day that we've never seen before. Reliability is absolutely critical to being able to move fast, change things, and innovate on the internet. If you don't have a reliable system, no one is going to let you push new features and run experiments. So let's go into some terminology. A GFE, or a Google front end, is a layer 7 load balancer that terminates user traffic such as HTTP, HTTPS, HTTP2, and HTTP3. There are two types, Google GFEs and Cloud GFEs. As you might expect, Google GFEs serve Google internal traffic, and Cloud GFEs serve Google Cloud load balancer traffic. Uber proxy is a proxy that is critical for Googlers to access internal systems. That includes monitoring, crash logs, and other debugging tools, as well as the ability to push jobs. QUIC is a new transport protocol that's built on top of UDP and is recently standardized at the IETF along with HTTP3, which runs over QUIC. GQuic, which stands for Google QUIC, was Google's experimental version of QUIC prior to standardization. It's a substantially different protocol, but it has many of the same features. And SRE stands for Site Reliability Engineer, which in this case has to respond to pages within 5 minutes, 24 hours a day, 7 days a week. To go over the issue, there's a query of depth that is triggered by resumption information sent from a GFE to a client back to different GFEs. At peak, around 10% of all Google GFEs were crashing, but it was very uneven, with most of them being in Europe. The total outage was 1 hour and 44 minutes, which is a very long time to have 10% of your fleet crashing. So, as I mentioned before, it was a query of depth, and it was a null pointer dereference. It was actually introduced in 2014. This code had been around for a very long time, had never been triggered before. It was an entirely new path, at least for us. The contagion, as we called it, and we'll go into that more later, occurred via clients. So what's key about this is the GFE gave out something that was encrypted with a key only it could decrypt. It gave it to the client. The client didn't know anything about it, and the client gave it back to the server. That meant that standard fuzzing and typical internet traffic could never actually trigger it. It was only a GFE that could crash another GFE via this indirect mechanism. That was the only way this was plausible. Initially, this looked absolutely terrifying. The SREs involved couldn't access any monitoring tools because Uber proxy was down, and they thought everything was down globally. And it looked like absolutely everything was on fire. They had no idea. It looked like a total global outage. This made it very slow to diagnose. They couldn't get to internal monitoring for over 1 hour. However, once they did, it was very fast. Mitigation only took 17 minutes. We also got very lucky in a number of ways. Only GFEs and data centers crashed, and only Google GFEs crashed. This could have been much worse. So let's go over what a contagion bug is. So this is really about an interaction of distributed systems. So typically at Google, we have slow rollouts with long canaries that find bugs before any real harm is done. If a bug is found, we just roll back the canary. Contagion bugs, however, are not fixed by rollbacks alone, as you'll hear later. A single task could actually cause a global outage in the worst case. And persistent state in another system is either hard or impossible to roll back. In the case of internet clients, you really have no control over the browsers out there and what they cache and what they don't. It's also not just crashes, and it's not just clients that can cause this. It can be almost any type of bug. It could be incorrect HTTP responses. It could be a memory leak, infinite loops. All these sort of bugs, and each have their different properties to make them better or worse to debug. Really, any 2 or more large-scale distributed systems are required, and they can be almost of any type. And sometimes it could take a very long time to actually notice and not be caught in canary. So crashes are very easy to identify, but incorrect responses are much harder to identify. So the example here is TLS or quick resumption. So in these cases, there's information given from the server about how to resume a TLS connection. So the next TLS connection is faster and saves a round trip. Similarly, for QUIC, there are things called source address tokens. They prove that the client owns a source address, and again, saves a round trip for future resumption and future connections. So one GFE gives the client information for a future connection, and then the client gives it back to a different GFE. And, typically this all goes well. So let's go into what happened in Google in November of 2021. So, as I said before, the browser contacted a canary machine that had a new flag, and the handshake was complete. Everything worked perfectly. The canary machine gave a token back to the client that it could save for future connections. As I said before, all GPs send this token, and it's encrypted. However, canary jobs happen to add a new field. So then the browser sends the token back to a different GFE. This GFE has a latent bug, as we talked about before, which is a null pointer deref. And it only happens if this new flag is false. So the canary GFEs are immune to it. They're not crashing. Only all the other GFEs are crashing. Ironically enough, if we had deployed this globally immediately, it also would have fixed the issue. Also, to make it worse, the token is supposed to be cleared after it's used once, even if the handshake does not complete. However, there was a bug in Chrome that caused token not to be cleared if the handshake didn't complete. So this just perpetuated. And once these tokens were given out, they just kept crashing more and more GFEs. So, as I said before, the client just keeps using the poison token, but it doesn't understand. Why is it that every time I talk to a GFE, it crashes? Okay. Well, try another GFE. Oh, that crashed too. There is one feature that did slightly mitigate the issue. When Chromium clients see a handshake failure, they mark QUIC as what is called broken and go into an exponential backoff. So they'll wait 5 minutes before trying QUIC again for that domain, 10 minutes before trying it again if that handshake fails, and so forth. But this takes a long time to kick in. And we gave out tokens for a lot of domains. And so for each one, Chrome is going to try it again and crash the GFE. So let's look at the timeline. This was rolled out at 27 past Pacific Standard Time to 4 machines. GFEs in Europe almost immediately began crashing. Probers started failing 4 minutes later, and SREs were paged. The canary judge, which can automatically roll things back, at that point rolled things back, which is very lucky. However, the GFEs just kept crashing. That didn't really help. The SREs realized that all of their tools, including crash logs and the ability to push any flags, were completely inaccessible. It took them almost an hour to realize this is not a global outage. It was only when they started being able to reach out to India and New Zealand SREs and ask them to reroute traffic for Uber proxy that they were able to really start root causing the issue. So then they disabled QUIC. And a few hours later, they paged me at 6 a.m. to try to figure out what the heck happened. So let's talk about why this took so long to mitigate. Uber proxy is only served from data centers, not from the edge. The SREs terminate on Google GFEs in Europe, but these were effectively down. As I said before, the outage was very regional. So a huge portion of those 10% of GFEs that were crashing were all in Europe. Uber proxy was barely usable and really not useful for debugging. So they didn't have crash logs, and all they knew was that they were getting paged, that GFEs were crashing, and probers were failing, and they didn't know why. But as I said before, they got lucky that they could contact some SREs in other locations and get help. However, more than an hour was lost in this issue just due to Uber proxy unavailability and not due to the issue itself being difficult to debug. So as I said before, crashes were largely only in Europe and only in data centers. So data center queries actually only dropped by 0.3% globally. So our systems were very good about routing away from these crashing GFEs and avoiding significant harm. However, a number of services were impacted: Gmail, groups, tasks, calendar, and chat. However, as I said before, Uber proxy was particularly impacted because it relies upon long-lived connections, not short-lived connections like many other Google services. Did make hacker news, unfortunately, but it was not nearly as bad as it first looked. So let's talk about what went well. The SREs were paged almost instantly, and the escalation worked perfectly. And once Uber proxy was back available and stack traces were available, the root cause was extremely fast, and the rollback was fast as well. Having cloud GFEs separate from Google GFEs meant there was no impact to cloud load balancer. This was very fortuitous. But we got lucky in some areas as well, which I'll talk about next. But SREs believe if Uber proxy hadn't gone down, this would have been a 20-minute outage that would not have been nearly as severe. We got incredibly lucky that the push was only active for 4 minutes on 4 tasks. However, 4 minutes times 4 tasks still managed to give out enough of these poison tokens to crash 10% of GFEs globally for over an hour. We were incredibly lucky that automated rollbacks caught a crash in a Canary GFE that hadn't received the flags yet. If it had crashed only a few minutes later, it might have received the flag and then it wouldn't have been crashing, and the automated rollback wouldn't have kicked in. The Cloud GFE Canary hadn't actually started, so Cloud GFEs were unaffected. Similarly, we hadn't pushed to Edge, so those were unaffected. Otherwise, we would have lost Google.com, YouTube.com, and a whole number of other domains. However, it wasn't just that. We also were able to use Meet, which wasn't served by GFEs, to triage the issue. And the big red button, which we used to disable QUIC, even though it hadn't been used in years, worked perfectly. So that allowed us to very quickly disable QUIC and get the fleet back to healthy, even though we could not actually flush the state in any of the clients. So SREs outside of Europe were able to use production tools and actually help the European SREs figure out what exactly was going on. So there were a number of follow-up action items, but let's highlight some interesting ones. We added more static analysis to try to look for C++ anti-patterns like potential null pointer derefs. We added quite a bit of extensive fuzzing, particularly around the crypto handshake, which is quite complex. And we targeted things that are inside the encryption envelope. So like this token, as I said, that the GFE encrypts for the client, and the client can't decrypt. So we specifically fuzz the token, and we specifically fuzz other things inside encryption envelopes. We also did some work to try to prevent contagion from ever happening. So we test one version of GFE against another version of GFE with realistic clients to simulate this GFE to client interaction that we observed. We also try to mitigate contagion. We regionalized some things, such as resumption. And we also updated the Canary judges. So we didn't have to rely on getting lucky and having a Canary machine crash right before it received the flag. And finally, we made sure that SREs can respond, because having this issue fixed in 20 minutes would have been incredible compared to having it fixed in an hour and 44 minutes. So we no longer serve Uber proxy from Canary locations, and we don't put Canary locations next to large SRE offices to make sure SREs are not impacted by Canaries. We also worked to improve what we can do without Uber proxy when it's not available. So to close, these contagion outages are something that really could affect almost any distributed system, particularly if it interacts with other systems, which almost all of them do. Potentially there's state stored in some other system. Potentially it's bad state. It gets replayed to a different set of your binaries, and they crash, or they go into an inf loop, or something else fails for them. So though we've encountered very few of these issues could be extremely severe and have the property of one machine taking down an entire fleet. And it definitely is lurking behind many, many systems. I'm Swett, and thank you very much for listening today.